So we're left at the point where it's trying to understand the way the problem is encoded, and so I'm still stuck with understanding the row J fields and the column J fields, because if you've got a 3x3 lattice, right, which is basically in the transverse fields, you've got that, right, because each of those lattice sides, I think they're called, if I remember well, it represents the interaction with the ferromagnetic interaction with an external field. Whereas for the when it comes to the J variable, or the variable, but the J component, so you've got horizontal and vertical, if I understood the problem well, and that's in this case why you've got a two-dimensional. That was like a two-dimensional lattice, right? Because you basically have. So the idea is that each of those sides, each of those elements, interacts with its neighbors, right? So you've got then the what is that? The the interaction within the rows and within the columns, but I can't find where this is written. Oh, here. No. Yeah. Two such links, one for the row links, one for the column links. Here's the code that we can use to generate random problem. Okay, so I just found it. It's here in the comments. Links within a row, links within a column. So it's confusing me. So the column J field seems fine, right? Because you've got 3 columns, and in each column you've got 2 interactions, right? So am I blue? So you've got this interaction and this interaction, right? This interaction, this interaction, this interaction, and this interaction. So that makes sense that you're represented this way. But why would you do the row links within a row with this representation when it's kind of sort of the same, right? I mean, you've got 3 rows, and within each row there are 2 interactions. But maybe because that's kind of these here, right? But maybe this is just a matter of representing it as a maybe it's just a matter of representing it as a 2x3, like a 2x3 matrix, or a 3x2 matrix, because 3x2 matrix, because this is basically we've got 1 1 minus 1 1 minus 1 1, right? And so effectively you do have, I mean, you could still I mean, yeah, you could still think of this as this is kind of, it's awkward to think it this way. Row 0, this would be row 1, this would be row 2, right? And then those are the 2 interactions. So I don't really, maybe what we have to dive into is the actual code here. How is the ansatz prepared? That's probably how is the ansatz prepared, and then maybe that's going to help me understand why it is represented this way. It's a pity it's not explained the other way around. But let's see. But you get it, right? So those are the J fields. The green is, you can call it J2, and then the blue would be like J1 or something like that. And then this thing here, it's not blue, but like, I don't know. pink. No, that's too close. Yellow. So this is the basically the little h in the Hamiltonian. Okay, I'll clean that up. And let's move on. So now it's the interesting part is, and I'm still a bit confused between the overall VQE and QAOA, which by the way I've read somewhere that it's you can pronounce that Kwawa, which is pretty weird. Um, so what, which one of them is a family of algorithms? Which one of them is a special case of the other? What's the relationship of them? This is maybe something that I could probably make a. It's one of the things that I want to end up making a video about before I close this whole thing, VQE and QAOA, Kwawa. And then obviously I've got still ahead of me all the choice of pursuing this continuous variable quantum computing thing or not, or just seeing it as a sort of another. At the end of the day, it's the same concept, right? You've got modes, and you've got modes, and you've got gates, and then you've got ways to measure. It's just probably the way you measure is a bit different, and so. But at the end of the day, it should be kind of the same. Uh, but okay, I'll stick with that. So, and I probably won't dive in there, or because if I dive in that direction too much later on, I think I'm just gonna get lost. I really want to stay in track with that kind of more generic, that kind of more standard, discrete quantum computing. So let's move ahead. Electron values will be different from, yeah, okay, we know that. So given this definition of the problem instance, we can now introduce our ansatz. Our ansatz will consist of one step of a circuit made up of, okay, so we've got steps. An X power gate, so an X gate. It's a rotation. So I think this is basically a rotation around the x-axis for the same parameter for all qubits. This is the method we've written above. Then apply a Z power gate for the same parameter for all qubits where the transverse field term H is +1. So here we start getting into the circuit, basically the ansatz basically being mapped to the particular problem being mapped to the ansatz. So if this is a Z power gate, so this is basically a Z rotation, right? Nothing I could do is I could try to do that with Quirk at a smaller scale, maybe. Anyway, so it sounds like maybe this is something about flagging. So you're flagging there where there's a positive ferromagnetic interference. At the end of the day, right? I mean, this circuit is gonna have. It's gonna have to be somewhat related to our Hamiltonian, isn't it? Because here I see this. Wait a second. So how did they come? So how did they do this? Because here you see a Z, and that's basically it's related to the age, right? So that's a transverse field. Mm-hmm. Classical problem to the quantum problem, optimizing minimizing the expectation value of the observable. Okay, but this is not clear. How do they get there? I mean, they're basically what they're basically saying here is, so you've got the parameters, and so they're turning this into a Z. But maybe this is just an arbitrary choice, because this is an actual part of your parameterization. So you're gonna put here, you're gonna optimize the angle you're gonna use here. It still feels a bit mind blowing somehow that this is anyhow working. So where are we here? So you've got the Z power gate. Okay, so but it kind of intuitively something that you could think of. So you're doing something to the, so you're making a different, you're kind of differentiating the ones where the field interaction is not +1 with +1. Okay, so it's only +1 -1. So 0 is not a possible number in the initial problem representation. So okay, so you do that here. Half turns, and I mean, half turns is going to be basically the parameter that you're going to play with in terms of optimization. Then apply a control Z, doesn't it? Because apply a controlled should be 3. Yeah. Apply a controlled Z rotation for the same parameter between all qubits where the coupling field term J is +1. If the field is -1, apply a control Z power gate conjugated by the X gates on all the qubits. So first of all, control Z rotation is going to need 2 qubits. So I'm assuming that those are the 2 qubits that basically are part of the J, because remember that the J field, the coupling field J is basically between 2 of those of the sites in the lattice, right? So I would assume that I'm assuming we're mapping 1 qubit equals to 1 site, and so if the relationship between 2 of them is +1, then we are doing a control Z between the 2. And in this case, it doesn't matter which one is the control and which one is the target, because as we know, that doesn't matter for the control Z. And if it's -1, we apply a control Z power gate conjugated by X gates on all qubits. And if the field is -1, we apply conjugated by. So does this mean exactly that we have? So here's examples. And you've got the X gates afterwards, or what? Looks like. Let's see. So let's take a look at the code in here that does this. Yields rotations about 1-1 conditioned on the JR and JC fields. So, but what it does is, so it iterates over the rows. There's a mistake in here, because that should be something else like JC column, right? I mean, it doesn't matter. They are just reusing the. I know JC row. Okay, JR row, JC row. That's correct. So it iterates over the JR, and then J row, and then basically it iterates over each of them, and then it says if this is -1, then the then basically you apply a so that's the -1 case. Okay, so you apply an X gate to that qubit and an X gate to the other qubit. Remember, we're referring to qubits as part of the grid, and that's why. Okay, that's why it comes in handy. Interesting. Okay, that's why the representation here comes in handy for the grid qubits, because basically it's the lattice that we have. So as we are dealing with the row and the row fields, the J row, so the JRIJ basically is between between qubit ij and the next qubit in the row. Okay. hmm And okay, so this is so you apply an X gate, and then you apply uh don't get it. Why is this applied twice? So you apply it before and after? Don't get it. Looks like, because here's you've got your gate, which is a control. So in the variable gate, you've got a control Z, and you basically apply it here in between. Okay, between this qubit and this qubit. Then okay, so but you're doing it next before and after, and then the same here. So at the end of the day, the way you encode these in here, it doesn't really matter, really. I mean, that's one of the things that I'll try. So in the next video, we'll just get the hands on the actual coding. They'll try to make some modifications, see what happens. But basically, there shouldn't be any, because it's just you're just iterating over those things, right? So here, the difference I see is that basically for the column interactions, what you're doing is you're of course, if your qubit, if your J element or the side is the IJ side, then the one it's interacting with is the IJ+1, because it's the one below, sort of is the one in the next within the column. But basically, it's my but maybe I know why. So see, the way this is, you're gonna enumerate, it just bothers me a bit. Just let me spend a bit more time on this. So this is basically saying that for each I and JR row, and you're enumerating JR, right? But JR is like these. So you basically have, you're iterating twice. The first for loop, it just gives two iterations. So you've got basically row 0 and row 1. Okay, but kind of makes sense, because so if you've got your lattice, you're basically saying no, it doesn't make sense, because then within each row you've got three elements. That's confusing. Am I just being stupid, or you have got 3 elements? Okay, but the I plus 1 is this is the only one you're getting plus 1, right? So because this is just for you. What I'm trying to figure out is, I mean, that's so basic. Row, and then you've got basically, maybe it's just the naming that's confusing me. So this is the row. This is the row. The row interactions, and you're getting. So within a row, okay. So you're going kind of this way, right? Of course. So and you're gonna iterate 3 times. That's kind of the second. That's the J, right? The J is gonna have 3 iterations, but the I is gonna have 2, right? Because you want to basically have the first one and the second one, and then the second, and then the second one and the third one. So that's why you've got the I plus 1 in here. Yeah, that makes sense. Whereas in the second case, man, that's really basic. You've got your lattice, and then here you go. Here you're going. Here you basically have got 3 elements, so the I is going to iterate 3 times. Yeah, because you're going this way, so you've got 3 columns. So you want to iterate 3 times, and then within each column you just want to iterate 2 times, like this one and this one. And yeah, it just makes sense. I think that's so basic that you're probably gonna think that I'm stupid. Um, yeah. So of course you're trading 3 columns, and then you've got 3 columns, 1 column, 2 columns, 3 columns, and each of them has 2 interactions. And then for the row fields, you basically that's what's confusing me. So you're iterating. You're iterating 2 times. You're iterating 2 times, and you iterate. Wait a second. You've got you iterate 2 times. My point is, I think we could just encode it in a similar way than the column J fields. I'm just thinking, why would you do it differently? Uh, uh, so you've got so in your first iteration, you've got 0, 0, and then you've got 3 value. Okay, because you have I get it. Because you have okay, so you basically have so this is your first iteration and this is your second iteration. Oh my god. Yeah. Okay, we'll try to rewrite this maybe to prove that I'm not stupid, but it's one of those things that I guess this is just a matter of preference. And just to think that this is burning so much of my time and it's not quantum at all anyway. It's one of those things like it's a matter of how you write stuff, I guess. You could just whatever. Good. So back to the actual problem. So you've got basically the where was I? Exactly. So you got those things in here. So basically, what this is saying is you've got basically um, there where there's a positive interaction between two sides, you have a control Z, and there where there's a negative interaction, you have a basically an X gate in both qubits. Then you have control Z, and then you have another X gate. So you're with that, what you're I think intuitively doing is you're just saying, it's kind of the opposite, right? Is the probably it's probably a big stretch to call it the opposite. But it's basically, let me open Quirk for a second. So let's imagine we've got those two qubits, right? And so we're talking about a control. I apply a control Z here, right? That's what you're kind of getting. So it's nothing. Uh, as long as you have a 1 and a 1, then you're getting a 1 and 1 with a phase shift, right? You have a plus and a plus. Basically, what this is doing is it's phase shifting the 1 1, right? So component of whatever. So if your state is 0 0, obviously there's no component. So if your state is 0 1, there's also no component. If your state is 1 0, there's also no 1 1 component. But in this case, there is. If you're getting into superpositions, then you obviously also have that component. Oh, wait a second, that's interesting. Oh yeah, but basically I think that's exactly okay. So here, oh no, wait a second. You're shifting everything. If it's I. Mm. Anyway, yeah, I'm using my mouse pad, so I can't really use the. Okay, so but what this is saying now is that what the other one is doing is basically doing these. So if there's a -1, it's doing this, which effectively kind of turns this user into 1 1 in this case, right? And then it just applies what, and then you apply another X. X. So basically, it's doing a phase shift on the 0, 0. So it's kind of the mirror, if you would call it this way, I think. Let's see if we can I do something like this and then apply the density, not the amplitudes here and here, and I guess it's going to be always fixed because yeah, but if this is 1, 1, yeah, no, let's not mess up with the with multiple registers in here. Oh. So you've got that, and if you've got a 1, 1, right, you basically have the phase shifting here is not, it's 0, right? So there's no phase shift. If you go plus plus, you basically have got a phase shift on the 0, 0. If you go minus minus, so it kind of shows the a mirror effect, which is probably, yeah, which is probably um, which is probably what you want to design this for, because those interactions are opposite, right? One is ferromagnetic and another one is anti-ferromagnetic, if I remember well. When so you're kind of mapping exactly that problem into a circuit somehow, and then expected by parameterizing those things, you will find yeah. Still, why you choose a Z and why you don't choose something else? And I don't quite understand the initial X rotation, for example. I guess this is just for the sake of um, adding that variability, right? So you're kind of building a circuit that basically physically almost represents like from at the diagram level, right? It represents really your problem. So the two sides that are related, you're kind of mapping them into mirrored controlled operations, so it reflects that concept. And then, but they're still parameterized, uh, so you can add that variability and then find exactly what are the parameters that give you the minimal energy, kind of, so to say. So this is indeed a Quawa strategy, in the sense that, I mean, I remember at least in the previous videos doing the Quawa for the maxcut problem, that this is really what you're kind of doing to some extent. You're also connecting with using control sets. You're connecting the vertices in a graph that are connected, right, or that are part of the same group. Something, no, they're connected, something like that. I don't remember exactly. Mm. But still, why does this intuitively work? Mm. It kind of at intuition level makes sense. You're mapping one problem um, into a quantum circuit. You're turning it into a quantum circuit and allowing certain variability within that problem, so that you can tweak here and there. But still, it feels a bit. It feels weird that actually works. I don't know. That's probably going to be next video. I mean, I understand now why why the mapping works this way, but I'm not so sure that I'm not so sure why it works. Right. So I understand the mapping, and I believe that this is just for pure variability. I understand the Z operations here are because of the external field. So those have some extra stuff in there. Those qubits have some extra um, influence, but I don't know. We'll see. So next step is understanding why, and maybe to understand why, we'll just run the simulation, maybe. And I think then what we'll do is we'll tweak a bit the code, and then play with the code and see if we can kind of understand a bit more, why this works. But maybe we'll read something at the same time as well. So parameters in the ansatz. Okay, we'll see. We'll see. But basically, this is so we understand now the mapping. Perfect. Cool.